This is the second formal lecture for the course PH 4113, Symmetry Methods in Physics. We are continuing with our discussion on group theory for physical applications, and today we are going to take a look at a few examples of groups. But first, let me just quickly recap the basic definition of groups that we had taken a look at in the last lecture. Just to remind you, a group G, star is an ordered pair where G is a set and star is a binary operation from G cross G to G. That is, it takes pairs of elements from G into G. But this operation has to obey four basic properties. The properties are closure, which, as I discussed in the last class, is automatically implied when you say star is a binary operation. And then you have associativity, the fact that you can put your brackets wherever you want, or you may even omit the brackets if you want. It doesn't make any difference to the final end product. The existence of an identity, that is, there has to be an element in the group G such that for all G, multiplying by this particular element E will not change G at all, and every element has to have an inverse. That is, there has to be an element G inverse for every G such that G multiplied by G inverse and G inverse multiplied by G has to be E. Of course, we also discussed the fact that G1, G2 in general does not have to be G2, G1. Abelian groups are special cases where G1, G2 is always equal to G2, G1, but the majority of groups actually are non-abelian. Let us now take a look at some examples of groups. Our first example is a very familiar one. It's just the set of real numbers R along with the operation plus, which is just the addition of ordinary real numbers. Now, while it should be sort of obvious why this is a group, let me quickly run through the defining properties. Closure is obvious because if you add two real numbers, you obviously do get a real number. Associativity is one of the properties of addition that we explained in some detail a while ago. The additive identity in this case, the element which when added to any other element leaves the latter unchanged, is nothing but our familiar number 0. And inverse for a given number in this case is none other than the negative of that number. Because when you take a real number x and add to it minus x, you definitely do get 0. So all the four properties do work out. Now at this point, let me also put in a notational comment here. Very often when we talk about an abelian group, the operation is written plus instead of star. And for an abelian group, it is customary to use the symbol 0 for the identity under this plus operation. And we often at the same time denote the inverse of a group element for an abelian group by minus G. So we essentially borrow the same notation as that for real numbers under addition. It's obvious that real numbers under addition is a commutative or abelian group because for ordinary addition, of course, a plus b is always the same as b plus a. Now our next example is also an abelian group. It's almost the same set of real numbers. Why almost will be clear soon. And the operation here is into, just multiplication, plain multiplication of real numbers. Here, again, if you multiply two real numbers, you do get a real number. If you don't have to check associativity because that's one of the obvious properties of multiplication of numbers. The identity in this case is just 1, the number 1, because 1 times any number is that number back. Now, what about the inverse? Well, does every real number have an inverse? This is where we hit a stumbling block. Almost every real number has a multiplicative inverse, has a number which when you multiply it by, you end up with 1. So for a number x, this inverse is just 1 by x. However, there is one real number which does not have a multiplicative inverse, and that obviously is 0, because no matter what number you multiply 0 by, you always have to get 0, you cannot get 1. So the set of all real numbers under multiplication is not a group. What is a group, however, is a set R set minus 0, which means take all non-zero real numbers and take multiplication as your operation. This is a group, because the one assembling block that we had, the 0, does not have a multiplicative inverse, whereas in a group every element has to have a multiplicative inverse. That assembling block is removed by just removing the number 0 from the real number line. So this is another group, again an abelian group. The next example is not an abelian group. It's again a rather familiar example. This is of the set of all invertible n by n real valued matrices. So these are square matrices with real numbers as elements. And if you multiply two square matrices of size n each, you of course get another square matrix of size n. More importantly, if both A and B, the two elements we're multiplying, are invertible, then the product AB is also invertible. So AB's inverse exists in the set. So GLNR is closed under product of matrices. Notice that here we did not mention what the operation star really is, but if you are saying that it's a set of matrices, the obvious operation is matrix product. So, as I said, very often we will confuse the set with the group because the product operation may be obvious from the context. Associativity is a definite property, is a well-known property of matrix multiplication. Identity, of course, the identity matrix, n by n identity matrix, is an invertible matrix, so it definitely is in this set. And by virtue of the definition, every matrix has an inverse, every invertible matrix has an inverse, but more importantly, that inverse is also in the set of all invertible matrices, because if A has an inverse B, then B also has an inverse, namely A itself. GLNR is one of the most important examples of groups that we are going to deal with. And as we all know, AB and BA are not usually equal for matrices. So this is not an abelian group. This is our first non-abelian example. Well, GLNC is an obvious extension. Again, n by n matrices, but here with complex entries. Of course, the identity, which has only real entries, is of course an element of GLNC, simply because real numbers are also complex numbers. So that does not prevent the identity from being a member of GLNC. It's trivial to see that GLNC is also a group. A slightly non-trivial example, SLNR is a subset of all of GLNR. The set of all invertible n by n real valued matrices, M which obeys this additional condition, det M or determinant of M is 1. Now how do we know that this is a group? Well, of course, once again we did not specify what the group operation is. Once again, because it's obvious from the context. Here the group operation is simply multiplication. Again, matrix multiplication. So let us quickly check whether the group properties hold. Closure, if I multiply two matrices with determinant 1, I get another matrix whose determinant obviously is 1, because determinant of a product of two matrices, det AB, is det A times det B. So if M1 and M2 are both elements of SL and R, then det M1 M2 is det M1 times det M2, and that's 1 times 1 equals 1. Associativity is of course something which is borrowed from the standard result that all matrix multiplication is associative. Identity, well, of course the identity matrix is an identity for matrix multiplication, but what is very important is identity happens to be a matrix with determinant plus 1. So SLNR contains the identity. And inverse, well, all these matrices having non-zero determinant must be invertible, but what is important is that matrix which is an inverse of an SLNR matrix is also itself an SLNR matrix because its determinant is 1 over determinant of the original matrix, which is 1 by 1, hence 1. So SLNR passes the test of being a group. If we had, for example, taken the example of, say, all matrices with determinant plus 2, it would not have passed the very first test. If you take two matrices of determinant 2 and multiply them together, you do not get a matrix with determinant 2, you end up with a matrix with determinant 4. So closure will not be possible. Well, if instead of saying the determinant is 2, if we said take all elements with even determinant, will that work? Well, it will not work because the last property, that of inverse, will fail because if you have a matrix with determinant 2, which is a matrix with even determinant, its inverse will exist, will be a matrix, but will have a determinant half, which is not an even number, it's not even an integer, so it will not be in your set. So, along with examples of things which are groups, it's easy to see when things will not be a group. Sometimes it's not so easy to see when things will not be a group, so you have to be careful that all the properties do hold. Well, if SLNR is there, can SLNC be far behind? The answer is no. SLNC is actually a subset of GLNC, which is also a group in its own right. And in fact, subsets which are groups in their own right are very, very important. They are called subgroups. We will discuss subgroups in a lot of detail later. Well, another group which is very, very important is ON. This will be a group of immense importance in physics. It's a set of all orthogonal n by n real valued matrices, that is, matrices which obey transpose of M is the inverse of M, and we will leave it as an exercise to show that this set also forms a group, again obviously under matrix multiplication. A further subset of ON is SON, which is a set of all orthogonal n by n real valued matrices with determinant 1. Again, this one is an easy exercise to show that this is a subgroup. That is at least a group in its own right. And the example that we started with, you take a geometric object or a physical object, you consider the set of all its symmetry operations with the multiplication star here being composition, that is, do one symmetry operation after another. That is a group. I think we have given enough arguments to establish that so far. And our final example, at least for the time being, is the set Sn of permutations of n objects. Now this is a very, very important group and we will need to discuss this in some detail. So that is what we will turn to next. Now before we start describing the group Sn in some detail, let me point out one very important thing about all these examples. Almost all of these examples, barring the last two, have underlying sets which have infinitely many elements. So they are all infinite groups. In the first half of this course, however, we are going to focus primarily on finite groups. Infinite groups are very important, and special kind of infinite groups called Lie groups are going to hold center stage in the next half of our course. However, for the time being, let me point out that almost all of these examples are infinite groups except for the set of all symmetry operations of a given geometric object. Usually is finite, though not always. So that could be a challenge for you. Think of a geometric object whose group of symmetry elements happen to be an infinite group. And the set Sn of a permutation of n objects, of course, has n factorial elements, so that's a finite group. Just to make the definition formal, a group which has a finite number of elements in the underlying set is called a finite group. Of course, an infinite group could be countably infinite or uncountably infinite, as the case may be, depending on the cardinality of the base set. And as we will see, Finite groups are much simpler to think about, but sometimes we have to move beyond them and move to infinite groups. And then some special infinite groups are still rather easy to handle. Lie groups, the kind of groups that occur in physics very, very often, being one very important example. Let us now take a look at Sn in some detail. Now, the set of all permutations of n objects is a very, very important example. So important, in fact, that we are going to devote some time to describing what this set is and ways of denoting permutations and so on. First things first, the name Sn. The set of permutations of n objects is called a symmetric group, which is why it's denoted by S, the letter capital S. Of course, n tells you how many objects are you permuting. For the more mathematically minded, a permutation is nothing but a one-to-one onto map or a bijection of a finite set onto itself. Of course, if you are going to do a one-to-one onto map, all you can do is rearrange the elements among themselves. Nothing else can be done. Now, how do you denote a permutation? There are several ways. One of them is if you have a map pi which takes 1, 2 up to n to itself, then you can denote it by this symbol. This is a symbol which you have already seen before, where instead of using 1, 2, 3 up to n, we had used the letters A, B and C, but the idea is the same. You write this in two row. This looks like a matrix. You write it in two rows. Below 1, you write what happens to 1 under the permutation. Below 2, you write what happens to 2 under the permutation, and so on. So any element I of the set has pi I written below it. That's how you denote the permutation pi. Now, that's not the only way to denote permutations. A permutation can also be denoted by what is called a cycle structure. So, to illustrate this, let us take a look at a particular example of a permutation of 7 elements. So here, let's start with the element 1. You could actually start anywhere you want, but just for the sake of definiteness, let's say we are going to start with the element 1 and follow what happens to it and subsequent terms along the permutation. What I mean is, let's take a look at what happens to 1. 1 goes to 7. Then we look at what happens to 7. 7 goes to 3. What happens to 3? 3 goes to 5. What happens to 5? 5 goes back to 1. So what you have is a cycle of 4 elements. 1 goes to 7, 7 goes to 3, 3 goes to 5, and 5 goes back to 1. So that is a cycle. That's one of the cycles in this permutation. It's actually called a 4 cycle because it has 4 elements in it. 1, 7, 3, 5, back to 1, but we don't write the back to 1 here. If you write 1, 7, 3, 5 in a round bracket, it means that it's a cycle in which 1 goes to 7, 7 goes to 3, 3 goes to 5, and 5 goes to 1. Well, after you finish with this cycle, there are other elements which are not in this cycle. So we have to next go and look at the rest. Since 2 is not in the cycle, let's look at what happens to 2. 2 goes to 2 itself. So that's one cycle. 2 goes to 2. Then let's look at 1, 2 is done, so is 3. Let's look at what happens to 4. 4 goes to 6. 6 goes to 4. So 4, 6 is a 2 cycle. So you have one 4 cycle, a single 1 cycle, and a single 2 cycle. This is another way using the cycles to denote the same permutation. And this particular way of denoting permutations actually will turn out to be very, very important later on in our course. So 1 goes to 7, 7 goes to 3, 3 goes to 5, 5 goes back to 1. 2 is a 1 cycle, it goes nowhere. Very often in the notation we will drop 1 cycles. We'll just write this as 1, 7, 3, 5, 4, 6. With the understanding that any number or any element of the original set which is not represented in the cycle structure does not change under this particular permutation. So this permutation has 1, 1 cycle, 1, 2 cycle, and 1, 4 cycle. Of course, other permutations will have different divisions of this, and it will turn out that the cycle structure will play a very important role in the theory of representations of the symmetric group, which is a very important part of our course, which we will discuss in some detail later. Now that we have described some examples in detail, let us go back to our very first example, the set of all symmetries of an equilateral triangle. There we talked about the fact that two symmetries done in succession will give rise to a symmetry, and that is how we realize that there is a group structure underlying this whole set. But the question could very well be, which precise operations can be done one after the other to get a precise result? So what is important is to have a multiplication table which tells us one element G1 when multiplied by G2 gives you which particular third element G3. So to understand how the group multiplication table can be built up for this particular symmetry group, let us go back to the geometrical scenario. Remember, we had three reflections which were symmetries, reflections in the line A, B and C. We also had three rotations, E, which was a rotation through 0 degrees, so no rotation at all, D, which was a rotation through 120 degrees, and F, a rotation through 240 degrees. So in the multiplication table, what we do is label each column with a header, which is a group element, and each row also with a group element, and a particular entry in the table, which, say for example, an entry here, which is in the row labeled by A and the column labeled by B, is actually A star B. Of course, that means you do B first, then you do A. So let us try to see how we can use the fact that we know what the symmetry operations do to an arbitrary point on the triangle to build up this multiplication table. Now, one row and one column of this multiplication table fill themselves up automatically, because E times anything is that thing back. Similarly, anything times E is that thing back. So this is what the multiplication table really contains. As I said, let's take this element. This is actually in the row labeled by B and the column labeled by C. So this is really B star C. But let's go back and see that this row and this column are trivial to fill up. These are the results that we have when you multiply any element by E on the left. So that's what you have here. And this is what you get when you multiply any element by E on the right. So we still have all these other entries of the multiplication table to fill up. So to see how you can fill up this particular column, this column has A on the right and followed by other elements. So basically this says you do A first, then you do the other stuff. So what we do is we do exactly what we did at the end of the triangle example. We pick an arbitrary point P and figure out what happens when you apply the various operations to P. EP, of course, is the point P itself. This is where the point P lands up when you do a reflection in this line. So this was where it was. Now it ends up here. That's AP. BP is where the point will land up if you reflect it in the line B. So just think of geometric reflection. This is where it's going to land up. CP, another reflection. If you rotate the entire triangle through 120 degrees, this point is going to go and land up here. That's DP. And 240 degrees is going to land up here. That's FP. So this is our stage. This is what we need to know before we can fill up the multiplication table. Now, filling up the multiplication table column-wise is pretty straightforward. The first column, of course, is already done. The second column, you start by doing A first. So you started with this point. Now I've dropped the P just to make writing down the thing a bit easier. I've just labeled every point by which group operation would take you to that point. So this is E, this is A, and so on. Now I've done A, so this is where you end up. If you do A again, that is, if you reflect this red point in this line, you're of course going to go back to the point E. So that's why A times A is E. Now, instead of doing that, if you did B after that, that is, if you reflected in this line, you would end up at F. So, B times A is F. Remember, the red point is what you get after you do A, and then if you do C, let's say, you're going to end up here, which is in D. If instead of doing any of the reflections you did D after you did A, you're going to rotate through 120 degrees and land up here at C. And finally, if you did F after doing A, you're going to land up all the way here, that's B. Now, in the same fashion, you can complete all the other columns. I'm just going to illustrate one more. So, here we do B first, that's the red point here, E goes here. And then if you do A, you end up at D. If you do B, you end up at E, and so on. If you do C, you end up here at F. If you do D, you end up here. If you do F, that is a 240 degree rotation, you will end up at the point C. And proceeding in this fashion, you can immediately complete the entire table. I'm not going to comment on every step. It's pretty easy and you should be able to figure out what happens at each stage yourself. If necessary, of course, you can see the video in slow motion and figure out where every point is going. This ultimately is the full group multiplication table for the set of symmetries of an equilateral triangle. Now that we have this full multiplication table of the set of symmetries of the equilateral triangle, we can use it to illustrate a very important property of all finite groups. If you take a look at this multiplication table carefully, you will find that each one of the rows here are essentially permutations of the same set E, A, B, C, D, F, which means every row is a rearrangement of the set of elements in the group. Not only that, every column is also a rearrangement. So, in a given row, no two elements are ever repeated. The same goes for every column. This is what is called the rearrangement theorem. This works not only for this particular group, this works for all finite groups, and it is pretty easy to see why. For example, if you look at the ith column, any one of the columns labeled by the element Gi, let's say C, then G star Gi and G prime star Gi, two elements in the column, can be equal only if and only if G is the same as G prime. Well, if G is the same as G prime, of course G star Gi and G prime star Gi has to be the same. However, it also works only if G is equal to G prime. Why? Simply because every group element has an inverse, so Gi has an inverse. Since Gi inverse exists, you can hit G star Gi and G prime star Gi on the right with Gi inverse. That will help you cancel out the Gi and you will end up with G equal to G prime if G star Gi is equal to G prime star Gi. And that means that there can be no repeats in a given column. Of course, the ith row differs from this only because Gi is sitting there on the left. So Gi star G equals Gi star G prime is what we need to look at. But that also will hold only if G equals G prime, because Gi inverse acts as an inverse of Gi and cancels out Gi when you hit both sides of this expression from the left. So, the columns are rearrangements of the set of group elements, so are the rows. So, in this lecture, we have defined what a group is, we have seen some examples of a group, and we have also gone on and taken a look at how to build up a multiplication table and proven one very important theorem in group theory, namely the rearrangement theorem. So that's all for this lecture. we are going to take a look at the issue of subgroups and other structures in a group in the next lecture. Armed with these results, we are now going to take a look at some of the very simplest groups that we can have. In fact, I'm going to provide you with a complete classification of groups of order 1, order 2 and order 3. Order here means the number of elements in the group. So let us look at the smallest group first. Now all groups must contain the identity element E. That's one of the basic properties of a group. What that means is obviously an empty set cannot be a group. To qualify as a group, a set must have at least one element, the one which is going to qualify as the identity. It turns out that a set which has only one element, which is the identity for a particular operation, is the smallest possible group. A group with only one single element, a rather trivial group, of course, but one which will play an important role in the structure of the theory, as you will see in the later lectures. The obvious multiplication table for this group has one row and one column, E, and of course the result has to be E itself because there is nothing else in your set. You can easily check that all the defining properties of the group are being obeyed by this particular multiplication table. That's really rather trivial. Now what happens if you have more than one element? Let us talk of a group of two elements. Elements E, of course, has to be there, and another element A. We are just calling the other element A. We could have called it anything else, and whatever we argue next will still work. Well, if we try writing down the multiplication table for this particular group, as in the previous example, for a much bigger group, the first row and the first column are easy to fill up. This one has to be EA, this one has to be EA. The only thing to be found out is what goes here. And from the rearrangement theorem, it's obvious what has to go here. Since you cannot repeat an element in a given row or a given column, this one has to be E. And that is the complete multiplication table for a two-element group. Notice that in this case I did not care about what the identities of the elements are. What are they really? Are they numbers? Are they operations? Are they matrices? I don't care. And I don't even care what the operation is. As long as you have a group with two elements, you must have this multiplication table. Every two-element group has to have the same multiplication table, which is why we say there is only one group with two elements. The precise form of the elements may very well change from example to example, but the group structure is exactly the same. So this group comes in many forms depending on what the precise nature of the elements and the multiplication rule are. So one example, in line with what we have already seen in this lecture, do nothing and reflect in a line. These could be our two elements E and A respectively, and it is very easy to check that this is a group. Of course, here when I say this is a group, the composition rule or the multiplication rule is composition. You do one operation after another. Now, a simpler example, if you just take the set of two numbers 1 and -1, and here the product rule is simply multiplication, ordinary multiplication of numbers, it's again easy to check that this multiplication table will follow if you were to replace E by 1 and A by -1. So that is one more example of this smallest two-element group, or not the smallest, but a two-element group. Well, I can have more complicated things. For example, I can have these two matrices, and under matrix multiplication, it's very, very easy to check that you are again going to have the same table. The only non-trivial thing to check here is what happens when you multiply this element, which we are calling A now, by itself. But if you remember any quantum mechanics, this is nothing but sigma 3, and as you all know, sigma 3 square is the identity back again. which means it's back to this matrix. So this multiplication table will work for this as well. In that, you can easily see that instead of using this particular matrix, I could have used sigma 2 or sigma 1, and it would still have worked out as a group, and the multiplication table for the group would have been exactly the same. Well, final example that we are going to talk about, not the last example possible, but the final example that we are going to talk about is a set of integers 0 and 1. And now we are going to consider this to be a group under addition, but addition of a special kind. This is addition modulo 2, which means whenever I reach 2, I subtract that out. Or I'm just going to talk about remainders, which you get when you divide by 2. So in this case, 0 plus 0 is of course 0. 0 plus 1 is 1. 1 plus 0 is also 1. Which obviously tells you that 0 is the identity for this. And and 1 plus 1, which would have given you 2 under ordinary addition, gives you 0. So this actually replicates the multiplication table out here. And it is this set which gives the group its formal name. This group is formally called Z2 or Z2, depending on how you would prefer to pronounce it. And Z2 is basically the group of integers 0 and 1 modulo 2, addition modulo 2. Okay, we next move on to 3 elements. And with 3 elements E, A and B, this is of course the part of the multiplication table that is obvious. Now, what about this particular element here? If you use the rearrangement theorem, you know that this element cannot be A. So it can be either A, E or B. So let's try putting E here. If you put E here, then automatically rearrangement theorem applied to this row will tell you this will have to be B. Applied to this column will tell you this will have to be B, because that's the only element which is left. But now you are running into trouble, because now you end up with this column and this row, both with 2 B's, which is not allowed. Rearrangement theorem once again. So you cannot choose E for this element. You have to choose B. So the rest of the table can now be filled up very easily using just the rearrangement theorem. If you look at this particular element, it has to be the only one which is left in this row, so it has to be E. Similarly, this one has to be the only element possible in this column. Since A and B are already taken, this has to be E. And this leaves us only one choice for this corner. It has to be A. So just using the rearrangement theorem, we can complete the multiplication table. This actually happens to be a pretty familiar group. If instead of E, A and B, you take the numbers 0, 1 and 2 and use addition modulo 3 as the operation, you end up with precisely this multiplication table. So this group, as you can see, is abelian simply because if you look down this diagonal, the multiplication table is symmetric. So on this side, for example, you have E into B. On the corresponding corner, you have B into E. Similarly, this is B into A, this is A into B. They are all equal. Now that's a standard way of identifying from the multiplication table whether a group is abelian or not. You just have to see whether it's symmetric under a reflection around this diagonal. As I said, this is the group Z3 or Z3, the set 0, 1, 2 under addition modulo 3. What I've illustrated here is just by following the basic properties which a group has, you can completely pinpoint the possibilities as far as groups of order 1, 2 and 3 are concerned. Now things get more complicated as you go higher and higher up. I'm not going to continue this any further, but if you tried it on your own, you would find that there are 2 possible multiplication tables. So 2 different group structures possible for groups of order 4. On the other hand, groups of order 5 will again have only 1 possible multiplication table apart from re-identifications. Well, all these groups, in fact up to order 5, all of these groups have to be abelian. In fact, at this point, let me also just inform you that the order of a finite group can tell you a lot of information about this particular group, and one of the major important bunch of theorems in abstract group theory, Sylow's theorems, deal with exactly that. However, those are really not our concern in this course, so I will not delve any further into that. In the next lecture, we are going to look at substructures which groups have, namely subgroups. So until then, bye.